first postulate of the kinetic molecular theory states that gases consist of a very large number of tiny spherical particles that are far apart from one another compared to their size. This means that the actual size of each gas particle is extremely small relative to the space between them. These gas particles can be either atoms, like helium, or molecules like oxygen or carbon dioxide. What is important is that these particles are not packed tightly like they are in solids or even in liquids. In a solid, particles are close together and vibrate in place. In a liquid, they're still close but can slide around each other. In a gas, particles are far apart and move freely. This distance is so large that most of the volume in a gas is actually just empty space. That's why gases are easily compressible. You can push the particles closer together without squishing the particles themselves. Because the actual particles take up so little space, their own volume is considered insignificant when compared to the huge amount of empty space between them. Kinetic molecular theory explains that gas particles are in a constant, rapid, and random motion. This motion is what gives gas its unique properties. These particles move in straight lines until they bump into either another particle or the wall of the container. Because of their fast movement, gas particles have a relatively high amount of kinetic energy. Kinetic energy is simply the energy of motion, how much energy something has because it's moving. Think of a crowded bumper car ride at an amusement park. Cars are constantly moving, colliding, bouncing, and zooming in random directions. That's what gas particles are doing all the time inside a container. Tells us that collisions between gas particles and between the particles and the container walls are elastic. An elastic collision means that no kinetic energy is lost during the collision. The particles may transfer energy between each other, just like two balls bouncing off one another, but the total kinetic energy remains the same. This means that the kinetic energy or speed of one particle could decrease, while the other particle's respective kinetic energy or speed would increase to balance out. Adding the two would still remain the same constant energy. And this is important because it helps gases maintain their energy over time, even though collisions are constantly happening. So although individual particles might slow down or speed up after a collision, the total energy within the system of a gas stays consistent. In theory, the fourth postulate tells us that there are no forces of attraction or repulsion between gas particles. This means that each particle moves completely on its own, without being pulled toward or pushed away from any other particles nearby. Even when two particles get close to each other, they don't slow down or change direction. They simply keep moving in straight lines unless they collide. However, in reality, real gases do have tiny attractive forces, especially at low temperatures, which is how they can condense into liquids. But in the ideal gas world of kinetic theory, we assume these forces don't exist at all. The fifth postulate explains that the average kinetic energy of gas particles depends on the temperature of the gas. As the temperature increases, the particles move faster, which means they have more kinetic energy. That's why heating a balloon makes it expand, as the particles are moving more quickly and hitting the walls with more force. But not all gas particles move at the same speed. Essentially, temperature tells us the average kinetic energy of all the particles in the gas sample. The relationship is directly proportional, so when we heat a gas, we're actually increasing how much energy the particles have on average.